Welcome back, everybody. What we're going to do now is we are going to look at the derivation of Master's equations for a sim undergoing Markovian dynamics. And this is going to be a whiteboard type derivation. So hang in there, and we're going to see now in this lecture. So just to recall, we're going to start from this equation where we connect rho at c plus delta at c to rho t using the definition of the derivative. And we want to have an approximation for the time derivative of rho, whereby rho is the density operator, under the assumptions that the evolution is Markovian. There is a superoperator transforming rho to rho t plus delta t. The superoperator can be written in the Krauss operator sum representation form. So these are the three assumptions that we are going to use to be able to derive our equation. So what we're going to do now is we're going to derive what we call the Lindblad form of the master equation. And for that purpose, we're going to make a simplification, which is like resetting the clock. Since these equations should be valid for all times, instead of taking rho t, we're going to take rho 0. And instead of taking rho t plus delta t, we're going to take rho delta t. And in this case, we have that rho t plus delta t equals rho t plus delta t rho dot t will become rho delta t equals to rho 0 plus delta t rho dot 0. So remember that we are intending to derive something which is going to give the evolution. And we have also assumed, so reminder for you, we have also assumed that rho delta t plus t is a superoperator applied to rho t. So here we are going to set t equals 0 as well. So this is a superoperator, so that you don't forget. So we have rho delta t is equal to s rho 0. And we have also assumed that S has a Krauss decomposition, meaning it needs to satisfy all sorts of properties which we have already discussed, and it can be written using a sum of Krauss operators. So we can say that rho delta t is equal S rho 0, whereby this superoperator can be written in this way: kj delta t rho 0 k dagger j delta t. So now we would like this and this to be equal, right? Because both are describing a time evolution. You're taking operator from 0 to delta t. And we would like this equation, where you wrote it in terms of cross decomposition and in terms of a superoperator, to be equal to this equation here. So let me copy this equation. We are moving here. So this needs to be equal. And for this to happen, you're going to verify that this holds, because you're going to work backwards. But for this to happen, there must be a cross operator given by k naught equals to 1 plus a delta t, where a is a linear operator. And we are going to write the remaining operators. So let me write as well remaining cross operators. We're going to write them as kj square root of delta t lj, where these are also linear operators. And we consider j from 1 to infinity in our sum, but k naught is going to be given like this. This means that we can write whole delta t as k naught k naught dagger plus sum from j going from 1 to infinity square root of delta t lj whole 0 square root of delta t lj dagger. Okay. So we're going to tidy up, and we're going to substitute here, put the identity operator. We're going to substitute this expression here and tidy up this a bit, because we can multiply things. So this is going to give us 1 plus delta t a whole here, identity not 1, whole 0, 1 plus delta t a dagger. Okay. Plus the rest, which can be written as delta t, multiplying these two square roots here and pulling it out of the sum. Sum from j going from 1 to infinity, lj whole 0, lj dagger. Fair enough, so far so good. So I'm interested now in computing this guy. So let me call it A, just that we know where we're going. And this is then going to be, if we open this up, whole 0 plus delta t a whole 0 plus whole 0 delta t a dagger plus delta t square a whole 0 a dagger. And this is of the order of delta t square, and we said we wanted to keep only up to the orders of delta t, so this is going to be neglected next. But if we write whole, just to recap, is going to look like this: whole naught, whole 0 plus delta t a whole 0 plus whole 0 a dagger plus whatever operators you have of the order of delta t square plus j from 1 to infinity. Here delta t, hang on, forgot. Delta t j lj whole 0 lj dagger. So this is going to be neglected because delta t is going to 0. And when we do that, then we find an expression which gives me whole delta t equals to whole 0 plus delta t a whole 0 plus whole 0 a dagger plus j going from 1 to infinity lj whole 0 lj dagger. And we want to compare now with that first expression which we got from the definition of the derivative. So comparison with whole delta t, which is whole 0 plus delta t whole dot 0. Okay, so can you see what is going on? We have one expression here that is just whole 0, and you have this expression here, I forgot delta t, which also has delta t and has all this. So we can say that whole dot 0 is a whole 0 plus whole 0 a dagger plus sum over j from 1 to infinity lj whole 0 lj dagger. So we have this operator L, and we can say the evolution is the same for all times. So we're going to go back in that approximation that we have made, not to carry too many extra terms. And we're going to say that the evolution should be the same for all times, which makes sense physically because it doesn't matter where you put your clock. It should be the same. So assumption, evolution is the same for all times. And this is something we need to have to be able to go back. So we're going back. So we set whole dot t. Okay, and this is going to give us whole dot t is a whole t plus whole t a dagger plus sum over j from 1 to infinity lj whole t lj dagger. So we have an expression describing the evolution of our equation. We have a super operator on the right hand side, which is what we wanted, right? But we still need to do a lot of tweaking. So just to recall, we wanted to have here derivative of our density operator is equal to a super operator applied to the density operator. So we do have here, if you wish, S whole, but we would like to do some tweaking. So tweaking, we're going to use the fact, don't forget A is linear, right? So any linear operator in our case A, can be decomposed as A equals B plus IC, whereby this is Hermitian, so B equals B dagger, and this is Hermitian, C equals C dagger. If you don't believe it, check. Any linear operator can be written like that. And we are going to do it in a way that is convenient for us. So we're going to write A equals to minus I divided by H bar, H plus M. We're coming back to what they mean. You're going to see as the time goes by. But here we have then that where H is equal to H dagger. Yeah, this is the Hamiltonian you're going to see. And M is equal to M dagger. Okay, so we have a linear operator A, not necessarily Hermitian, but we can write it as a sum like this of two Hermitian operators. It's a complex operator in principle. And this means then that K naught is going to be 1, here identity plus delta T, minus I H bar H plus M, whereby both are Hermitian. And now we want to calculate what this mysterious M is. So can we calculate M? Can we discover what this is going to mean and how can we write this? So this is a bit mysterious, right? And to do that, we're going to use this property that sum over Kj dagger, Kj is equal to the identity operator. So we know then that K0 dagger, K0 plus some j from 1 to infinity, Kj dagger, Kj is equal to the identity operator. Fair enough. So we're going to use this to find M. So let me write this. We want to find, if we can find H is also nice, but we're going to focus on M. So this is our task. And let's do it then. So we're going to focus on K naught. So we're going to have a look at this. And we have then that K naught, dagger K naught, is equal to identity plus delta T I H I over H bar H plus M multiplied by 1 or identity plus delta T minus I H over H bar plus M. Now remember that this is actually all of this is K naught dagger. If you look at the expression that we had for K, we can see that K naught dagger, we know H is equal to H dagger, M is equal to M dagger, so it's going to be 1 plus delta T. Now, I over H dagger, which is equal to H plus M dagger. So this is what we had below, just that is clear. And This rest here is k. So opening this up, we find, this is k is 0, sorry, not k. Opening this up, we find that this is then equal to 1 identity plus delta t IH divided by H bar plus M plus delta T minus IH divided by H bar plus M plus something which is going to be of the order of delta T square, which we are going to neglect because we are assuming that delta T is going to 0 or is very, very infinitesimally small. Okay, now if you tidy this up, you see that we can add these things. So these two, they are going to cancel out, and we will end up with an expression then that is going to be k0 dagger k0 is identity operator plus 2 delta t, and you have this operator m. So if you put back and you consider everything which was in that condition for the Krauss decomposition, so back to some kj dagger kj is equal to the identity, we have then that identity plus 2 delta t m plus delta t sum from j going to from 1 to infinity lj dagger lj is equal to the identity operator. This here is going to cancel out. We can rearrange it, and we can say, we can also get rid of this guy. No, not the 2, the delta t. Simplify once it cancelled out. So we can say that 2m is equal to minus sum from j from 1 to infinity lj dagger lj. So what we know, I forgot, then you have m divided by minus 1/2 sum over j from 1 to infinity lj dagger lj. We don't know yet what these operators are, but we found a value for m, which is this Hermitian operator that we use to construct k0. And this is based on the property that the sum of k dagger k, whereby these are the Krauss operators, is the identity. So we have enough now to write our evolution equation. So we're gonna go back to our evolution equation. So back to the evolution equation of Rho. And what we'll find is that Rho dot t can be written as minus IH divided by H bar minus 1/2, inserting now the value of m, j from 1 to infinity, lj dash, lj dagger, lj, Rho t plus Rho t, I divided by H bar H minus 1/2, j going from 1 to infinity, lj dagger, lj. which is that part we had assumed that we had this k 0 dagger k, plus the rest, which is sum from j going from 1 to infinity, Lj whole t Lj dagger. Now note the following, note the form of this thing. We could say that this is an effective Hamiltonian. And if it's an effective Hamiltonian, you can also see that this is going to be a non-Hermitian Hamiltonian, because you're composing it using two Hermitian operators. But when you take the dagger, dagger is not going to be equal to H. So I'm going to define HF. So let us define. This is an important point as well. Defining an effective Hamiltonian. So what we're going to do is we're going to call HF is going to be H minus I H bar over 2 J from 1 to infinity Lj dagger Lj. And if you take the dagger, you're going to have H dagger, which is H. But I'm going to write this slowly. J from 1 to infinity. Now, if you do Lj dagger Lj dagger, so this is going to be equal to H, and this is going to be Lj dagger dagger, which is Lj. Okay. So can you see that this effective Hamiltonian is non-Hermitian? Because you can see, let me write this, so non-Hermitian, because HF dagger is different from HF. It's interesting. I'm mentioning this, we're going to come back to this when we look at applications, but I'm mentioning this so that you can understand what is going on. And we have defined then effective Hamiltonians, and you can see the shape that this equation, where we have here the time derivative, and here we have a super operator, you can see what kind of shape it's taking. And yes, we wrote it in a way that was convenient for us to be able to define it in that shape. Right? So this means that here is more like a side remark. Please note. So this means that minus I divided by H bar, H effective is minus I divided by H bar H minus 1/2 J from 1 to infinity Lj dagger Lj, because here what you have is you are going to multiply I H bar by minus I divided by H bar. So you got these guys here. You multiply here, you're going to have minus 1, and then you have a plus. Actually, then here this should be a plus, sorry. So we're going also to need I divided by H effective dagger, which is something that we had on top. So if we calculate I times H, H effective dagger, we get that this is going to be, now with the dagger, let's see, we change this sign, as you can see. So it's going to be I divided by H bar H plus, you have a minus sign, no, you have a plus sign, plus I times I, and here you have a H, and here you have a H divided by 2, so cut this, here we have a minus 1, and sum over L from J equals 1 to infinity, Lj dagger, Lj. So why are we doing this? Because we can write, if we plug this, using this definition in here, so let me cut this and then we can have a look. No, I wanted to copy, not cut. So let's paste and let's see how things go. So this bit, which is in front of ho, can be written as minus I H bar H effective. And if you look, actually coming back to here, we see that this sign here is not quite correct, because you have minus I multiplied by minus I, so we're gonna have minus 1. And we can see then that we have this expression for I divided by H bar H effective. So we can then conclude that this part here is minus I H bar H effective in our density operator. And we can also say that this other part is equal to I H bar H effective dagger. And because of that, we can see that our operator can be written as ho dash t minus I over H bar, so pulling this factor here and this factor out, H effective ho t minus ho t H effective dagger plus the rest, which is j equal 1 to infinity Lj ho t Lj dagger. And this that we have just derived here is called the Lindblad form of the master equation. So So we have assumed here, just to recap, that the evolution of the system was Markovian. And that we can describe the evolution of the system in an environment by a Krauss decomposition superoperator. And now we're going to have a look at what happens if these jump operators are set to 0, or this Lj. So this is a particular case which is going to give us information about the system's behavior. So we're going to assume that Lj are set to 0, and we're going to ask the question of what happens if they vanish. We can look, we see that H effective, let's look at the expression of H effective and H effective dagger. So I'm going to copy them here, copy, paste. So we can see that H effective is H minus I H bar divided by 2 Lj Lj. So if they vanish, then we can say that this term is going to disappear, so that H effective is going to be H. The same is going to happen to H effective dagger. And because we are assuming that H is Hermitian, we can say that H dagger is equal to H. So from here, we can say that we simplify quite a bit. We're going to go back to that. And the other consequence is that this third term, which we have in our evolution operator, in our evolution equation for the density operator, is going to be such that it's going to vanish as well. So we can say also that L from 1 to infinity, Lj rho t, Lj dagger is going to be 0. So what happens to that equation? Let's have a look. I'll copy this equation, which is the master equation in the Lindblad form. And we're going to paste it, and we're going to make these things disappear. So paste, move here, copy it too much. So we said this term is going to be, so this also goes away. Very good. So we said that this term is equal to 0. So this is going to vanish. And we said that HF is going to be equals to H, and HF dagger 2. So in the end, we can say that this equation reduces to dot to rho dot t minus I h bar h rho t minus rho t h, which is the commutator of h with rho t. And this is nothing else but the von Neumann equation, which we have defined and derived in the first lecture in which we started to discuss open quantum systems. So you can see also that this is something somehow you expected, because this is the evolution equation for a closed quantum system. And here I need to put emphasis on closed. So you see that all these other terms and all this effective Hamiltonian, which was non-Hermitian and was getting in this first term, that these come from the coupling with the environment, in fact. And these things, they have consequences. And we can see by looking at this limit that we can see that H is the Hamiltonian of the system we are interested in, but the system alone. You don't have any influence of the environment. If you could totally decouple the environment, the Hamiltonian, which would give you the whole evolution of this thing, would be H. However, you have some irreversible dynamics because you are connecting to the environment via these H, via these L operators. So Lj operators are responsible for the irreversible dynamics due to the coupling with the environment. So we brought this effective dynamics via these L operators by making a series of assumptions that we have used then to derive an effective evolution equation. And if you look, you can see that this is present here in this HF, which was an effective Hamiltonian we derived, and is present on this extra term. So we can really see that the coupling with the environment has been incorporated. And one observation here is that Lj are called jump operators. So these are operators that represent processes that are associated with the coupling with the environment. And we're going to see some examples. This is something mathematical, but we are going to see some examples next. So in our next lecture, we are going to see how these jump operators and how this formalism that we have just derived applies to light matter interaction, and in particular spontaneous emission. And this is going to illustrate also how you can interpret certain things that you get, like decay. So I hope you enjoy, and see you next.